almost time. So hello everybody. It's very nice to see you for the first Conflang in person, but second edition actually. And it all started a bit more than 3 years ago, I think, when we were working on that configuration language at my place, and we wanted to talk about it, but realized that there was no real venue for that. And so we said, why not just create one? So I just sent random emails to all the language creators, and Jürgen, who will come soon, I hope, and Mark, the other chairs, that did SCConfig, which was a similar event and configuration 2 years before. And everybody said yes. So for the first thing, we were like 7 people in the committee, which was a bit much, but still was really nice to see. And yeah, I think it was a success, at least from my perspective. So it's really cool to do the second edition now. And we will listen to Thomas, who will talk about Docker Smell and their impact.
Hello, everyone. Is the microphone working? Perfect. Today I will talk to you about a small study that I did on the impact of Docker Smell. I was a bit curious to see what's happening on Docker because it's quite popular in companies, and but it's loved mostly because it's loved by developers, according to Stack Overflow. It's the most wanted language configuration of programming language, and the most loved one. But when we dig a bit deeper inside the projects about Docker itself, we see that the knowledge of how to create a proper Docker file is not really well known by the community. According to Jürgen, 84% of 70,000 Docker files contain some type of violations, at least on open source projects. And when we compare Docker files created by experts compared to a normal folks on GitHub, there is 5 times more violations inside open source Docker files compared to, for example, Docker file created by the Docker organization, which is quite a lot. And so I was a bit curious to know what type of impact those Docker Smell can have on the project itself. And this, I identify kind of 3 types of impact. Mostly, there is the image. You can create bloats inside the Docker file. You can reduce the reliability, and you can reduce the security of the project. But for this talk, I will mostly focus on the image size, mostly because it's the only metric that I can really measure reliably. And basically, and I will divide the talk in 2 main parts. One, I will discuss on how to detect those smells and repair them. And then the second aspect, I will analyze what is the impact of smell before and after by removing the smell, basically. And I decided to detect and repair instead of injecting a Docker smell because I do want to contribute to the community and provide additional knowledge, just having a tool that can display the smell and say, oh, that is a potential fix for you. But yeah, let's dig in the detection and repairs part of the talk. There is multiple related work that try to do some type of repairs or detection of smells inside the Docker community. We have some master theses that try to fix misconfiguration. We have some human in the loop repairs, but most interesting, there is an XC paper of 2020, which try to understand and learns DevOps artifacts in Docker, and I want to talk a bit more about this paper because I will inspire myself of this contribution in order to create my study. This paper worked mostly with 3 different steps. The first one is parsing the Docker files and bash. It's quite traditional, but what is the interesting part is they increase the abstraction of their models by injecting information about the commands of the Docker. For example, if you apt-get install, you will identify that you try to install package, and you can identify easily which package you install. And it's based on this annotation of the model, you can relatively easily do queries and create some rule-based analysis to identify the smell. relatively easily with relatively clear, clear patterns. And for the evaluation, they basically look at GitHub and try to find a bunch load of Dockerfiles. In this case, they will identify 108,000 different ones. And they also identify Dockerfiles created by gold samples, mostly from organizations that are used to write Dockerfiles. In this case, mostly Docker, basically. And then they wrote 23 different rules to detect those smells. Those are the rules, and the interesting part of it is that they kind of identify which rules are visible or not in expert Dockerfiles, and that way they can create a confidence level on which rules is problematic or not. And this we have a good set confidence, and we can see that some of the rules are really respected in gold samples, while it's not respected in the general community. They have create kind of a model of what rules should be fixed or not. In my work, I kind of inspire myself quite a lot of this contribution, and I mostly for the bash command annotation, because most rules are related to some commands, and just having this augmentation of the model is quite interesting. And I also use the rules that they presented. But I kind of improve a bit the contribution by including more rules, by also being able to repair those smells. Also, I can completely re-implement the approach and to be completely AST based. That way I can reconstruct the source code, I can do the modification of the AST. This is a bit more reusable by the community. I also support like nested commands like sudo apt-get. That way I can also still analyzing it, and I can also support some conditions and so on. And in order to compare a bit the performance of my tool compared to them, I compare the precision recall of the both tools, and basically we are both good. But more interestingly, I did the detection and the repairs on a big data set of their data set plus mine, and then I compared both the data sets, and I show that I succeed to repair most of the smell, with the exception of one of them, where I was a bit more protective, because I knew that this rule would break the build if I fix it too aggressively. And here you have the top 20 rules detected. This is mostly related to installation of package, npm apt-get install, and the use of caching. In Docker, you need to remove the cache in order to reduce the Docker image, and you need to do it in one single line, which is really not something that people are used to do in interactive bash. And that's why we see as such, let's go back to this slide, such a gap between the knowledge of practitioners, of normal people that are using bash, and people that are doing Docker. And we can see in this column which rules is a common practice in interactive bash compared to what should be applied in Docker. And we see that most of them are no. That's where the problems of sharing the knowledge between what you should do in Docker and what is actually done in practice is a bit problematic. Yes, I wanted to do a quick demo. It's not super impressive, but I think it's quite nice to see what the tool looks like and what I was aiming to do. I wrote this tool in TypeScript, mostly to be able to portability and sharing information, and also to integrate in Visual Studio Code. And basically we have a Dockerfile on the side, and then we have all the rules that have been detected, and you can actually patch it. And it's also quite nice to see the extracting some knowledge, but also all the type of AST that exists, all the type of annotation that we extracted from the Dockerfile. For example, we know we have literals, we have apt-get package installed. That we can extract just by querying this annotation, and we get all the package that actually install inside the Docker. This is quite easy interface if you want to parse Bash and Dockerfiles, for example. That's basically about the detection and repair that I wanted to present. Do you have any questions, comments right now? Okay. Oh, good. This I can move to the study part of that what I did. There's the goal. There is two main goals on this study: is kind of analyzing the impact of the Docker smell and identify which smell are more likely to create the most impact. And I also wanted to kind of get the perspective of developers, because if the developers don't care about those smells, if you don't, there is kind of no point of fixing them. For that, I had to create a new data set of buildable Docker image. I look at which Dockerfile contain at least one violations. I only find 13,000 of them, and I only succeed to build 6,000 of them. This is already quite a big problematic of rebuilding Docker image of random repositories. And after that, once I succeed to build the Docker image, I do apply automatically the repair of the smell, and I build it, and 369 of them are failing due to my repairs. And this is the tables of which type of rules introduce the most regression inside the building. The first rule is mostly due to because I install package without the recommended package, which surprisingly doesn't break that many builds, only 312 on the 6,000 of them. It also means that developers are relying on recommended. This is relatively optional. This is maybe something that to investigate in the future to see which package are actually needed, and maybe to declare them explicitly in your Dockerfile to increase reliability. Also have some issues by once I remove the cache of apt-get, and it's still used later on Dockerfiles. It's one for basically developers don't respect the good practice of installing all your package in the same single lines and then using apt-get update and then install and then remove your caches. If you remove the cache a bit earlier and you try to install something later on, your build will crash. This is something that will require more advanced refactoring that I didn't support yet. It's planned in the future. Now I discuss about the impact, mostly on the size. On the 6,000 Docker files, and we have a bunch of issues, and I succeed to measure the image size before and after. And basically, by using my technique, I succeed to save 277 gigabytes, this 5% on average of the complete Docker images. And this is the compressed size of Docker. It's not the uncompressed Docker image. And we see that our median is quite low with 1.1 megabytes, but with some really huge one with 6 gigabytes of saving for some image. This is not revolutionary. It will not save a lot of space for a lot of projects, but for some projects it's really useful. And I will discuss a bit some examples on open source project. Yeah, and then also look at a bit Docker image. When you build a Docker image, you want to deploy it on DockerHub to make it available, and you want to reuse it and deploy it. So I kind of look at what are the impact on terms of bandwidth, and we see that I have like I notify 1,600 images that are actually deployed on DockerHub, and I have something like 4 billion downloads. And if we consider the safe saving, I would save like 40 terabytes a week just on 1,600 image. And this is quite interesting that even small changes can have relatively big impact on terms of bandwidth. And I do expect that something at Google scale with much more built and much more bigger registry, this type of impact can increase even more. that showed quite a bit of potential. I was quite happy with that, and I decided to open a bunch of pull requests to see a bit the feedback of the developers. I opened 35 pull requests, but one of the projects had been removed since, so I have 34 now. Thank you, open source projects. I select a bit randomly cherry picking a project by looking at projects that are accepting a contribution. I don't have a long sign up of license agreements and things like that. Only had to do it one for the number 26, who took almost a year to get merged because I had to sign documents and then sign it again and finally be in the Jira list. Just have Jira issues to say, oh, we should look at this, and then finally they merged it last week, I think. That was my victory. We have quite a lot of variety of projects, from a small project with 2 stars and a relatively big project with 6,000 stars. And the image saving is from gigabytes of saving to few data save. Yes. This will have from few percent of saving until like 10, 16, or 40% of saving just by applying those simple smell repairs. And developers was pretty happy that that's some comment that I received. They say, oh yeah, that's pretty nice contribution. Can you also apply it on my base image, because that would save, would apply for all my projects. Also, you teach me something about Bash, that's pretty nice. This is my initial goal of introducing new information to the community. It's working relatively well, and people seem to be really quite happy. I only had to reject, mostly because they say, oh, we already have Alpine version, just, we don't really care about that, or it's already in production for somehow. That basically, what I'm taking of that is that developers really cares about those changes. They consider it when they know about it. And the only reason that I get rejected is because I already implemented it. The main takeaway of this study is that smells can relatively be easily patched, because there is not much really complex things in those smells, and the patch that you can do is relatively straightforward, and we can find a bunch of examples on GitHub, and you just follow what developers are doing. We still need a bit more to be a bit more fancy in terms of analysis to be sure that the patch doesn't break the build, or do more advanced refactoring, like grouping all the apt get installed together and identify what will be the impact on the project. Also, this Docker smell introduce quite a lot of bloats, like around 5%, but this can relatively be easily mitigated. And most importantly for me is that developers care about those changes. I was expecting a bit more reluctance about the smell, because when we talk about smell to developers, most of them say, yeah, we don't really care, it's just false positive. But in this case, they seem to be quite receptive about it. Thus maybe this type of smell are relatively precise enough and with relatively low false positive and really quite actionable that the developers really care about it. And also, my other takeaway is that developers don't know the good practices. And that's having tools like that kind of give them what they should do relatively straight in a direct way could be quite positive for them. Yeah, my next step for this type of work is kind of try to predict the impact of a smell. I do a static analysis of the Dockerfile and say, oh, you identify those smells. I predict that you have 1 gigabyte of bloat inside your image. Because I realized that providing this information to the developer really motivates them to actually do something about it. And just say, oh, fix that, and without providing the feedback is problematic. Also plan to apply some additional rules. Identify some interesting one that I want to do it, mostly in security. I realize that developers are still using a lot of HTTP inside Docker image, especially to define the registry for the package. Does it mean that you could really easily do injection of malicious content inside Docker image, which is problematic and surprising. And also, I would like to find a way to analyze the reliability and security impact of those mail. But I'm not sure exactly how to do that. If you have some ideas, just let me know. But probably we're more like a case study, and we'll see. And also, I want to share that I have 2 open positions at TU Delft. One about the testing and automatic maintenance of Docker, if you know someone that would be interesting to do that. And also, we are starting a new lab with JetBrains on introducing more runtime information inside the IDE. If also someone, if you know a PhD student that wants to do some runtime analysis and patch generation or feedback information to developers, just let me know. Yeah, that's basically the end of my talk. If you have any question, I think I have a few seconds right now to answer them, otherwise it will be a bit later on. And thank you very much.
Thanks a lot. Yes, we have a bit of time for questions, but also keep your questions written down because we have a dedicated time at the end. But if anyone has an immediate question.
Sure. Okay. Yeah. So thank you. That's a really cool talk and a super interesting perspective here. Can you say a little bit more about the fix space? So what do these fixes look like? Are they mostly sort of semantics preserving? Are they sometimes more complex?
They're pretty simple. They don't always preserve semantic. For example, if you say, I want to remove the cache, if you install something at runtime, you can have a problem. But, or if you remove the recommended package, if you depend on it, your runtime can actually crash. That's why I need a bit more advanced analysis, not only on the Dockerfile, but also on the application. And there is quite a lot of debloating tools for Docker image. And this I would like to use a bit those approach with maybe coverage, kind of also with some dynamic information. But most of them are quite safe, like removing cache from npm, because normally in PM when you install it in the root folders and also in your repository. This you can remove one of them to save space and stuff like that.
How much discussion do you see about this in the pull requests? Like, were there people like, hey, I have to check what you're actually doing here? Or were they like, oh, this looks simple and good?
Most of them just click on merge without any comments. Some a bit more advanced project kind of say, how can you analyze if we really don't need those dependencies? And some of them ask me to remove, for example, the non-recommendation. They ask me to remove that specific patch. And you consider just keeping the one from NPM, keeping them from pip, and just removing the one from installation of the recommendation. Because they kind of, some people know a bit more about it and just a bit more careful, and also depend on the complexity of the project. The project that asked me that was really low-level compilation based, and this compared to just a web application that just provide content.
Okay, very cool work.
Thank you.